Okay, good morning. So we have been discussing about air conditioning systems in the previous class, and initially we discussed about the simple air conditioning system. And in case of simple air conditioning system, if this is our room, then we were having some room sensible heat load and room latent heat load, which was actually entering the room, and our air conditioning system must remove the same amount of heat in order to same amount of heat and moisture in order to maintain the room at the indoor temperature and humidity conditions. For that purpose, what we have done, we have recirculated the m dot as mass of the air, and we have passed this m dot as mass of the air over the cooling coil, and in this cooling coil uh, its temperature and humidity were reached to Ts and Ws conditions, and then we allowed it to enter the room. So when the m dot as is entering at Ts and Ws conditions, where Ts is less than Ti and Ws is less than Wi, then whatever this external load is coming on the room, it actually takes that external load and again at temperature Ti comes out of the room. So it's simple, like some cold air is actually blown from one duct. That cold air, while it is moving from one corner to other corner, it is actually taking the heat from the room and again maintaining the room at the Ti condition, and at Ti condition from other duct actually it is taken out, and then this recirculation is in continuous process. Is this point clear? However, in this case, we do not have at any point of time addition of fresh air from outside. So that's why this type of system will be able to maintain the temperature and humidity, but it will not be able to produce breathable air, because ultimately what will be happening, after longer duration of same quantity of air, the concentration of CO2 will be increasing and some other pollutants or say odor etc will be actually becoming troublesome for the human comfort conditions. Okay, so that's why what we typically do whenever we design the air conditioning system, we allow some amount of air actually to bypass. Okay, so bypass means we will be not bypass, we allow some amount of fresh air to actually enter into the room. So whenever we are allowing some amount of fresh air, of course the fresh air is coming from the ambient condition, so it comes at temperature TO, which is greater than the temperature of the recirculated air. So that's why it will be causing some additional load. And when we are bringing this air, we have to also remove certain amount of air. So equivalent amount of air actually we are rejecting outside from the room, and that air we are supplying again at temperature Ti, which is again less than the temperature of ambient condition. So it means these two are coming as nothing but some additional load on the system. Okay, now whenever we do air conditioning system, of course we have some finite value of bypass factor. However, bypass factor makes the analysis bit complicated. That's why initially we will be discussing the summer air conditioning system with ventilation and zero bypass factor, because once this is clear to us, then we can go for the further complexity of including the finite amount of bypass factor. When we have zero bypass factor, it means that the entire volume of the air is in perfect contact with the cooling coil, and the entire air exit state will be equal to that of the apparatus dew point temperature. Is this point clear? Okay, so in this case, again the diagram is identical to the similar to the simple system. The only difference is that whatever this m dot as amount of air is there, it entire is not passed through the cooling coil. Only m dot ar amount is recirculated, whereas m dot a naught amount is dumped to the ambient condition, whereas the equivalent amount of fresh air is taken from the ambient, which initially is at condition O, and this I and O mix together to form condition 1, and after point 1 what we have then we have supply state 2, which is entering into the room. Is this one clear? Okay, now in this case I can simply write that m dot as from mass balance, if I take at this point, then m dot as is nothing but equal to m dot ar plus m dot a naught. Anyone is having any doubt about this? Okay. Other than this, if you see what I can write, I can also write energy balance. So if I write energy balance at this point, then it simply becomes that m dot a naught is coming with Cp moisture and T naught plus m dot ar is coming with Cp moisture and Ti. Okay, and finally the entire mass is becoming m dot as, and what it is becoming? It is becoming state number 1. So which simply means Cpma into T1. Anyone is having any doubt about this? Or in simple sense, I can simply write it in the form of enthalpies. Let me write m dot a naught into h naught plus m dot ar into hi equal to m dot as into h1. Is this one clear? So enthalpy is only written as Cp of moisture into temperature. So this is, say, equation number 1, this is equation number 2. Equation number 2 is energy balance at this point. Now, some amount of heat is actually removed in the cooling coil also. Okay. So, what is the load on cooling coil? Cooling coil will be removing heat. It will be taking heat from the system, and then it will be cooling the air from state 1 to state 2. Is this one clear? So that Q can be simply written as m dot as into H1 minus H2. Anyone is having any doubt about this? If I write energy equation for cooling coil is basically removing, say, Q amount of heat. Q amount is, say, load on the cooling coil. So that load is nothing but m dot as mass is passing over the cooling coil, and we assume that we have what? We have? Zero bypass factor. So what will be the apparatus dew point temperature? Same will be the T2 temperature. Okay. But let me write in general sense m dot as into H1 minus H2. All are clear with this point? Now what will happen? Now I can write Q is equal to, in place of m dot as, I can write m dot ar plus m dot a naught. Into H1 minus H2. Is this one clear? Or let me do it other way. Let me first write it like this: m dot as into H1 minus m dot as into H2 separately. Now what you do, m dot as into H1 from equation 2, how you can write? From equation 2, m dot as into H1 can be written as m dot a naught h naught plus ar hi, okay, minus of, in place of m dot as, now you write m dot ar plus m dot a naught into h2. Okay. So from here, if I do further simplification, I will be getting that Q is equal to m dot ar into hi minus h2. Is this one clear? Plus m dot a naught into h naught minus h2. All are clear with this point? Please tell me. Now what is m dot ar into hi minus h2? If you see the schematic diagram, m dot ar is nothing but the mass of the recirculated air. M dot ar is mass of the recirculated air of the room, and this recirculated air is coming at temperature Ti and going out of the cooling coil at temperature T2. Okay, so first term simply represents m dot ar into Hi minus H2. What is this? This is nothing but room total heat. RTH. This is the total heat load of the room. And if you see the second term, it is m dot A naught. M dot A naught is coming from here. It is coming at temperature T naught and going out at temperature T2. So on the cooling coil, it is creating a load of 0 to 2. So m dot A naught into H naught minus H2. So this was room total heat load. This can be written as outside air total heat. All are clear with this point or not? Are you getting this point? So it means that whatever the load is there on the cooling coil, that load is the sum of load caused by the recirculated air from the room plus load caused by the external air which is taken from the ambient. So the room air is recirculated from state I to state 2. That's why its load will be m dot ar into Hi minus H2, whereas the other one is taken at m dot A naught, ambient air with mass flow rate of m dot A naught, and H naught minus H2 is the load. So the total heat load on the cooling coil will be total heat load of the room air which is recirculated plus the outside air heat load. Is this one clear? Now if I have to convert this load into cooling load, into sensible load, and the how much will be the sensible load? 0.0204 QVR, recirculated air. Okay, QVR into Ti minus T2. How much will be the outside air load? Please tell me. 0.0204 into QV naught. Okay, so corresponding to MA naught, say volumetric flow rate is QV naught. QV naught into T naught minus T2. Clear? And how much will be the latent load? Please tell me. 50 into Wi minus correct? So this is the latent load. Okay. So now the combination of room total heat plus outside air total heat is something which is known as grand total heat, GTH. What we call this? Grand total heat. This is called as grand sensible heat. GSH, and this is called as GLH. Okay, the way we define room sensible heat factor, in the similar way I can define grand sensible heat factor, and grand sensible heat factor is nothing but equal to grand sensible heat divided by GSH plus GLH. Okay, Is this point clear? All are agreeing to this point or not? Clear? Now, if you have to represent all these processes on the psychometric chart, how you can represent? How to start? Say this is my state I. What state I is representing? Conditions of indoor. So this will be corresponding to indoor temperature and indoor humidity. Then what I will be having? I will be having outdoor condition. Outdoor temperature and humidity will always be greater than the indoor temperature and humidity for summer air conditioning applications. Okay, we are talking about over here summer air conditioning applications. So in summer, outside humidity and temperature is always greater in comparison to indoor temperature and humidity. So that's why my outdoor condition will be somewhere over here. Say this is my outdoor temperature and this is my outdoor humidity. Is this one clear? Now, what typically happens before the air moves over the cooling coil, mixing of outside air and indoor recirculated air is taking place. Is this one here? Indoor recirculated air and outside air are mixing together. So it means that their final, and this is a adiabatic mixing. I do not have any heat transfer before the cooling coil. So this is a adiabatic mixing. Whenever I have adiabatic mixing, my final state must lie on the straight line joining these 2 points. Okay. So let me join these 2 points with a straight line. Now what will happen? I will be having my state 1. State 1 is the state of the supply air just before the cooling coil. Okay. So after mixing. So after mixing, whatever state 1 I will be getting, that can be closer to state 1 if the mass of recirculated air is more in comparison to the mass of fresh air added, and if mass of fresh air added is more, then it will be towards O. But usually the amount of external air added is less, because if you add more amount of external air, then it will be creating more load on the cooling coil. All are clear with this point? Yes. So what will happen? I will be having state 1 somewhere over here. See, close to the state I, but where it should be exactly located at present, I don't know. Is this point clear? All are clear with this point or not? Now, I can calculate the value of grand sensible heat factor. Okay. So if I calculate value of grand sensible heat factor, then from alignment circle with sensible heat factor scale, I can draw a line, and parallel to that I can move a line which is passing through which point? Point 1. Okay. Parallel to that I can move a line which is passing through point 1. So from point 1 I will be having some line like this. Another important point is, this is the supply air, but whenever this supply air flow rate is chosen, it is chosen in such a way so that it should also satisfy the room sensible heat equation and the room latent heat equation. Is this point clear? Please tell me this point, because this 1 to this particular line I have drawn simply by considering the load from 1 to 2, which is the grand total load. But ultimately, the grand total load should adjust itself in such a way so that the room total heat load equation should also satisfy. Is this point clear? Room total heat load equation should also simultaneously satisfy, because if room total heat load equation is not satisfied, then ultimately you will not be able to maintain TIWI. Your TIWI will be different. So it means that the supply state of the air which is entering the room, that must lie at the intersection of grand sensible heat factor line and the room sensible heat factor line. Is this point clear or not? You have to understand this point very clearly. Okay. Whatever is the grand load on the cooling coil, that grand load should supply the supply air at the state which is satisfying actually the room total heat load condition. So that's why whatever this grand sensible heat factor line is there, this and RSHF line will be intersecting at a point, and that intersection will be deciding the supply state. Is this point clear? However, you have to remember one point, that this present case we are considering with nothing but the zero bypass factor. Present case we are considering with zero bypass factor. What it means? It means that the supply state will be corresponding to apparatus dew point. Apparatus dew point always lie on the saturated curve. So that's why the room sensible heat factor line must also intersect the saturated saturated curve at a point where grand sensible heat factor line is intersecting. Is this point clear? Then only the common intersection point will be established. All are clear with this point or not? So this is important to understand actually. So this is nothing but my ADP, TADP, apparatus dew point. All are clear? Now arrows are also very important, and in present case ADP will also represent the state. Which state? State 2. My supply state as per schematic is state 2. I have zero bypass factor, that's why supply state will also be this. Okay, and this point is the intersection of grand sensible heat factor line and the room sensible heat factor line. Now the arrow will also represent one important thing. When I represented 1 to 2 line, I am marking arrow in this direction. What it shows? It shows state of air at state 1 is cooled to state 2. Now what is happening state 2? At state 2 air is entering the room, and in other side of the room that is becoming one I enter. Okay, I state I. So it means 2 to I line must have arrow in this direction. Okay, so I to 2 arrow represents that the supplied air over the cooling coil is actually cooled down from state 1 to state 2, whereas the arrow 2 to I represents that the supplied air to the room is heated from temperature 2, supply temperature 2 to temperature I. Is this one clear? Now the line 1 to 2, where this line is taking the load, line 1 to 2 is taking the load over the cooling coil. Okay, so cooling coil must take the entire load. So that's why 1 to 2 line is nothing but the line of what? Grand sensible heat factor. 1 to 2 line is of grand sensible heat factor. Whereas what 2 to I is doing? 2 to I is simply taking the load of the room sensible heat plus room latent heat load it is taking. So that's why I to 2 line represents the room sensible heat factor line. Is this point clear or not? All are understanding this point? So it is representing room sensible heat factor line. Now it is important to understand, in case of simple system, what was unknown? If you have to note down the number of unknowns, in case of simple system, what were unknowns? Please tell me. Q, Vs, TS and WS. These were unknowns. Now one more unknown has been added. What is that unknown? QV naught. Either QV naught or QVR. Anything. That will be deciding. Let me write QVR. Because if I know QVR, that how much of supplied air is recirculated, then QV naught will be easily known to me. That will be nothing but QVS minus Q. Is this point clear? All are agreeing to this point or not? Now, you have to simply understand one important point. That QVS, TS and WS, these were calculated based on the These were calculated by how many equations? Two equations, which were room sensible heat factor equation and room latent heat load equation. Okay. Along with that, now we have grand sensible heat load and grand total heat load equation. So these two will also be coming into picture. That's why the supply state must be the intersection of these two lines. Is this point clear or not? Do you agree to this point? Okay. What I said, these three first we were able to calculate only from two equations. How we were calculating only from two equations? Because for chosen value of QVS, there were unique supply states TS and WS. Okay. Yes. For given QVS, supply states were fixed. Then, if for given QVS I have fixed the TS and WS, then with the TS and WS and the QVS, I will be checking if it is satisfying my room sensible heat load or room latent heat load. If it is satisfying, solution is fine. If not satisfying, let me change the QVS. Correct? This point is clear? Yes. Now, along with the QVS, I have to also change QVR. Okay, so it means I need more equation. So more equation is coming as nothing but grand sensible heat load or grand sensible latent load equation. Okay. So that is the reason now whatever the grand load on cooling coil is there, that is deciding the supply state. But ultimately that supply state should be capable enough to take the room latent heat load and room sensible heat load. That's why the supply state is nothing but the intersection of the grand sensible heat factor and the room sensible heat factor. Is this point clear? Now, same system, summer air conditioning system. But this summer air conditioning is with ventilation and with bypass factor. Now, bypass factor is not 0. You have finite value of bypass factor. What will happen in this scenario? Please tell me. Can you do it now?
Supply state will not be ADP.
Yes. State I state O let's assume this is state 1. Then one line I will be having from 1 to this. This will be my ADP. And I will be having one more line from intersection of these two lines to point I. and this will be my supply state 2. When this is my supply state 2, then this will be representing my bypass factor x, and this must represent my 1 minus x with reference to 1. What is this line? Black colored line? GSHF line, and green colored line is nothing but over here RSHF line. Okay, but is this solution so much straightforward? Is this solution such a straightforward? No. Why? Because you have to satisfy now 3 things. One more constraint is added. First was that it must satisfy the GSHF and RSHF line, so that's why it should lie on the intersection of the 2 lines, GSHF and RSHF. At the same point of time, it must also satisfy the given value of the bypass factor. And what is the given value of bypass factor? X will be equal to T2 minus TADP upon T1 minus TADP. Is this point clear? So it must also satisfy X as well. Okay. So again, see, right, if I simply give you this is X, this is that, then it will be very simple. Numerical values. If calibrated numerical values are given such that all parameters are satisfied. But if you have to design something, then it will be again a challenging problem. Okay. So here what you need to do? You need to follow the iterative process. Okay. How iterative process? Say you have taken certain amount of QVS and QV0. Corresponding to that QVS and QV0, you have calculated value of GSHF. That GSHF you have drawn over here. And then after putting that GSHF over here, you found that this line comes the RSHF will be remaining fixed always, because room latent heat load and sensible heat load is known to us. Okay, so this RSHF, this green line will always remain fixed, but GSHF can vary depending upon the amount of ambient air which we are adding. Okay, based on that recirculated air we can change. Okay, so if I change that, then state 1 can change. Is this point clear? Yes. So what I can do, I can take a first trial where I have taken some value for state 1. Corresponding to that state 1, what I have done? I have drawn the GSHF line. And then I found that this is state 2 is becoming my intersection of GSHF and RSHF line. Okay, and when I will be extending further this GSHF line to saturated curve, it will be representing my ADP. Clear? All are clear with this point? Now, I will be in opinion that point 2 should be my supply state. Correct? But whatever this supply state is there, that supply state should satisfy the bypass factor of the cooling coil. Okay, now I must check that when I am getting this state 2 using this equation, if my value of bypass factor is being satisfied or not. If the value is not satisfied, what it means? this grand sensible heat factor line will not be able to give me state number 2 out of the cooling coil. Then what I need to do? I may need to change the inlet state. Corresponding to inlet state, I will be getting some another GSHF line. Then this intersection may be somewhere over here. So this may become my new supply state 2 dash. There I will be checking. If this is not satisfying, then I may come to this point. Then intersection is over here. So like this, what I need to do? I need to follow multiple iterations, and out of these multiple iterations, what I will be able to do? The grand sensible heat factor line, which gives me supply state by intersection with the room sensible heat factor line in such a way that also satisfy the bypass factor of the cooling coil, that will be my actual solution. Is this point clear or not? Okay, so this process will be very complicated because you have to follow multiple iterations. Is this point clear? All are clear with this point or not? Okay, now there comes one approximate method. There comes one approximate method, and this approximate method saves us from following this iterative process. And this approximate method is something which is called as effective room sensible heat factor. So this approximate method is effective room sensible heat factor method, which saves us from this iterative process. All are clear with this point? So in this process, what I will do, I will first draw the same schematic diagram but in slightly different fashion. This is my room on which RSH and RLH is there, and it is maintained at Ti and Wi. Okay? All are clear with this point? Now somewhere over here, let me consider my cooling coil. So I have two types of air. One is QV naught air, correct? One is QV. These two are coming. All are fine with this? These two are coming. But ultimately what is happening? When these two are coming, these are not perfectly passing over the cooling coil. Okay? How much fraction of them is in perfect contact with the cooling coil? 1 minus x fraction. Only 1 minus x is in perfect contact with cooling coil and x fraction is not in contact. So I can say that out of this, only 1 minus x into QV naught is in perfect contact, and from this side 1 minus x into QVR is in perfect contact with the cooling coil, correct? Then the remaining portion of this is x into QVR, correct? This x into QVR is going as it is. All are clear with this point or not? Without any change in temperature, this is going. Similarly, from here, what is going? X into QV naught, correct? Now out of the cooling coil, say here my state is 2 dash. First, with the 2 dash state QVR is mixed, and after that here my remaining state is mixed, and then finally I get state 2. Okay, and what is this state 2? What is this state 2? State 2 must have QV naught plus QVR, which is the supply, that will be entering the room. Is this one clear or not? And of course, this same amount will be taking out of the room, from which only QVR amount is taken here and QV naught amount is sent outside. Getting my point or not? So this is actually the effective system. Okay, it means that actual load on the cooling coil is not exactly the entire outside air load. It is basically some fraction of outside air load. Is this point clear? So this way, what I can do on this cooling coil, I can define effective sensible heat load, and effective sensible heat load can be given as the combination of room sensible heat load plus what? X times of outside air sensible heat. Is this one clear or not? Shall we do some numerical problems? Do we have time for that or not? Is this one clear? Now, how this adds up? Please tell me. What we can do now, the way you have earlier calculated, sensible heat factor, room sensible heat factor and grand sensible heat factor, you can simply calculate effective sensible heat load as factor as ESH divided by ESH plus ELH. Okay, is this one clear? So in this way, what I will be having on the psychometric chart, I have now 3 lines. this is GSHF, this is RSHF, and this is ESHF. And here there will be one 2-day state which typically corresponding to state 2. Let us understand this with the help of one numerical problem. Shall we do numerical problem? Understanding about this effective room sensible heat factor, because if we do it conceptually it will be confusing for you, so let us do it with the help of a numerical problem. Okay, so but the question is, shall I directly do problem on ESHF, or before shall we first do the problems with simple system and then shall we come over this?
Simple.
So first you want simple problem or you want to do it by your own? One simple problem?
Yes.
Okay, let me then give you the problem statement. So this effective one I will explain you with the help of numerical problem more precisely. Okay, just rough estimate I have given. Now let me first give you the idea of some numerical problem. Let us try. Problem number 1 is, I am reading the statement and key important point I will be writing over here. Okay, so the indoor design conditions are 25 degrees Celsius and 50% relative humidity. What it means? Indoor design conditions are 25 degrees Celsius. It means Ti is equal to 25, Wi is equal to 25%. Okay. The RSH and RLH are 100 kilowatt and 20 kilowatt respectively. How much is RSH? And RLH is 20 kilowatt respectively. First thing we have to find the minimum volume flow rate and the volume flow rate at supply temperature of 14 degrees Celsius, 15 degrees Celsius and 16 degrees Celsius. Okay, so what is the first question? What we need to define? Minimum volume flow rate. And second part of this is, means in first question itself, the next part is volume flow rates of supply air at 3 different temperatures: 14 degrees Celsius, 15 degrees Celsius and 16 degrees Celsius. Then part 2 is, if the bypass factor of the cooling coil is 0.15, X is equal to 0.15. Find the supply air state and the volume flow rate. Okay, let me, before going for the numerical problem, let me tell you one important aspect. Okay. You see, in this question, there are two numbers are given, RSH and RLH. Their values are 100 watt and, sorry, was it watt? Oh, kilowatt. 100 kilowatt and 20 kilowatt. Okay. So what it means? From where these numbers are coming? From where these numbers are coming? How much will be RSH and how much will be RLH on the room?
Calculate like tube lights. Estimate.
We have to calculate the heating load or cooling load estimation. Okay, so if you recall, to all of you, I have circulated the Excel sheet and in that topics are written. Okay, and what are the topics? All for all 7 groups?
Sensible.
Heating load estimation, not sensible, design of heating load estimation. What it means? In the similar way, the question could be cooling load estimation, because I have given you for the buildings of the colder regions, so that's why I have asked heating load. So basically, this RSH and RLH are actually the values which are coming from the heating load or cooling load estimation analysis. Okay. So whatever the numerical problems, or whatever the project problems I have given to you, in all the project problems, after going through the building height, width, then length, thickness of wall, how many windows, how many doors, what filtration could take place. After doing the detailed analysis, you will be finally calculating in your project the heating load. Okay, and that heating load will be nothing but in the form of room sensible load and the latent load. Is this one clear? So, from all the projects for different buildings, you should tell me the values of RSH and RLH. When you will be telling the value of RSH and RLH, after that, what we can do? If RSH and RLH is known to me, then I can design the air conditioning system. That what type of air conditioning system I will be requiring. How much amount of air I need to recirculate. Okay. So all these things will be coming after I know the value of RSH and RLH. So in this numerical problem, RSH and RLH are given to us. It means what we need to do, we directly need to design the air conditioning system. Is this one clear? All are clear with this or not? So why I told you, because ultimately you need to again submit the project reports for that one. So their final outcome should be RSH and RLH. Is this one clear? Okay, maybe do you have class after this? Okay, so all of you can practice this problem. In the next class we will do the numerical problems related to the air conditioning system design. Okay, but you can try this problem. This is very simple problem for the simple air conditioning system.